Okay, Assalamualaikum and good morning. So, before we start today's lecture, let me remind you that you have to submit your second assignment tomorrow. So I will create a folder for that. And your second test should be on the following Thursday. Okay, hope there's nothing. That's week, today is week 10. Can anyone confirm?
Yes, Afternoon.
Okay, so we'll have it in week 11 then. Okay. All right. So today we continue with the lectures that we had before, where we stop at the case of Compton scattering. So let me go. So this, and I think we've come to the point where we are actually doing this. We have introduced the notation before. Let's recall the previous, well, first we have the incoming particles, okay, which is denoted for their form momenta denoted by P. So there will be two of them in this particular case, one for the photons and one for the electron, okay. And then the form momenta for the particles after the collision is denoted by Q. And again, over here, the one with the subscript bracket 1 is the photon with the wiggly line. And then the solid straight line is given by, is for the electron, sorry. Okay. So the other thing that we have mentioned previously is that for the photons, essentially your form momenta is going to be a null vector. So when you contract this form momenta with its covariant part, then you get 0, because essentially form momenta in general will give you minus m squared c squared, where m here is the rest mass. And similarly for the case of q1 mu, which is again for the photon, so you get 0 scalar here. For the electrons, you have essentially it follows this one, which is then given by the mass of electron, the rest mass of electron, me squared c squared. Okay. One of the things that we all have also mentioned is the fact that for photons, we can always write your form momenta in this simplified manner, where you have the three momenta of the photon and the fourth component. The fourth component is given by the magnitude of this momenta. So when essentially you do the P mu 1, P mu, okay, so you get P dot P minus P squared. But P dot P is essentially P squared. So P squared minus P squared will be equal to 0. Okay, so this is essentially the form, the general form for a particle with 0 mass. Okay, so it always has this form of having the momenta, the three momenta here, and then the fourth component would be just the magnitude of that three momenta. So you can see the same for the case of the form momenta of the photon after the collision. Okay. So so today, okay, the other thing is about the electron. So here we give the symbol Pe for the three momenta, and QE for the one after the collision. And for the fourth component, we just write is this has the relativistic energy here, E divided by C, and to differentiate for the one after the collision will be just adding a dash. Okay. So so let's try to do the Compton scattering conservation of four momenta. So essentially, in this case, we do the case of the incoming electron will be at rest. So in other words, the electron is at rest, and then a photon sort of bombards the electron, and then after that, essentially your photon gets scattered and your electron also gets scattered. Okay. So in that particular case, then your PE over here, your initial momenta for the electron, will be given as 0, as the 0 vector. And then your relativistic energy will just be your rest mass energy. Okay. Remember, the relativistic energy could include the kinetic energy in general, okay, which is given by that. But then here we put your PE to be 0 over here, so it would be just your rest mass energy. So so conservation of your four momenta. So in other words, over here will be P mu plus 1, P mu 2 will be equals to Q1 mu plus Q2 mu. Okay, so taking the components, the three momenta will get conserved, and then this will be given by this equation, because your initial momenta for electron is 0, so you get only your photon momenta. Excuse me for a while. Sorry, cat matters. So your three momenta will be just your photon momenta for the initial case, which is going to be equals to the three momenta of the photon equals to the three momenta of your photon plus the three momenta of your electron after the collision. Okay. So so that is for the first three components. For the fourth component, it will be given by this magnitude of the three momenta of photon plus the rest mass energy, okay, equals to the magnitude of the three momenta of the photon after the collision plus the relativistic energy of electron after the collision divided by C. Okay. So what we're going to do with all this equation is we are going to sort of manipulate it to get essentially what we call Compton formula. Okay. So remember, where have you heard about Compton scattering? Is the case of showing the electromagnetic waves essentially is like a particle. I hope you have done that in the course of modern physics. So in other words, when it interacts with other particles, the electromagnetic waves are just like ordinary particles. Okay, so that was the essential idea of this Compton formula and Compton scattering phenomena. So what we're going to do next is to manipulate these two equations so that you'll get the formula for your Compton scattering. So let's rearrange this in a way we write this in terms, we write an expression for your electron energy after the collision. Okay, so this is just bringing your Q onto the other side. And then you have to remember that E dash over C was given by this earlier. Okay, so this, remember, is coming from your relativistic energy, which is inclusive of your rest mass energy and your kinetic energy. Okay, so so let's equate them both. So here you have a square root. So what one can do is to square it. Okay, we square the two expression over here. Okay, so you get P plus MEC minus Q squared, and then squaring on the right hand side will just remove the square root. Okay, and then you expand this square, so essentially you get all the terms with the squared term here and then the cross terms. Okay, so these are the cross terms. Okay, and then you can see that, okay, this thing also appears on the other side, so you can cancel them on both sides. Okay, so what's left are just the cross terms. Okay, so for this we'll try to make the connection of this P dot Q with this PQ. So one uses a formula that you have seen for the case of vector calculus. Okay, so we use P dot Q when it's written in terms of the magnitudes will be just PQ cos theta, where theta is essentially the angle between your momenta of your, sorry, it's not your momenta of electron. This would be the initial, so this initial momenta of photon. So if you continue with this direction, and then you compare with the final momenta of the photon. Okay, so that angle here is the angle between the final momenta of photon with the initial momenta of the photon. So that is essentially the scattering angle of photons. Okay, so you write in that sense, and then we plug this thing into the equation over here. So this becomes PQ cos theta, and then remember that we have another PQ here, so you can bring it on this other side. Okay, so you get PQ 1 minus cos theta, and then the rest of the term will be this cross term here and this cross term here, which you can pull out the factor, the common factor of MEC, and then this would be P minus Q. And then the other thing that we have done over in this equation is to divide by 2. So you have all the common factor of 2 there. Okay, so you're left with this equation, which we can now rearrange. So you divide this whole equation by divide this equation by PQ, so that removes that PQ. So you get 1 minus cos theta, and then MEC, and P divided by PQ gives you 1 over Q, and Q divided by PQ gives 1 over P. Okay, so we are almost close to the point of reproducing your Compton scattering formula. But we need some other input over here, because if you remember, the Compton scattering formula are expressed in terms of either the frequency or the wavelength of the photon. So here we just simply use the frequency here, for example, okay, where we have to get the input of quantum mechanics, where E equals to h nu, okay, this is the Planck's formula, and then in terms of relativistic idea of what the energy is supposed to be, is going to be E equals to PC. Where is this coming from? This is coming from here. Remember, this is m squared c squared plus, let me just recall that properly, because I can't remember the square of, yeah, it's square. And then, sorry, your Momenta square. I always get confused with the, so I think that should be right. Yeah. So then when your mass of the photon is 0, so you get just P. So that's not quite right. I think there should be some, let me just check over here. I think this is actually wrong. Oh, this is right, sorry. This is right, but I've forgotten I have one with C there. So really, if I want to re-express in terms of the energy, then this should be m squared c squared, sorry, c to the fourth, because you bring on c to the other side, so pulling it into the square root, that gives you c to the fourth, and then p squared c squared. That makes more sense. So in other words, what we have in this case of the photon, you just have your m equals 0, so this should be a c squared here. So mass of the photon is 0, so that's 0. So you just E equals to PC. Okay, so that is the equation over here. So now one can re-express the P in terms of the frequency, which is given by here for the case of the momenta before the collision, and Q here is the momenta of the photon after the collision. So in order to differentiate the frequency before and after, you use the one before just nu, and the one after the collision is just nu dash. So you plug this into the formula here, so you have, by right, you should be having, here should be C over H nu dash, and then here will be C over H nu. So you can bring out your factor of C and C over H outside, so you get that. So this is essentially the Compton formula. You may have seen this in terms of the wavelength. So what's the connection between wavelength of a photon and the frequency of photon? Anyone can remember? Maybe I should see if everyone's still awake. Anyone can remember what's the connection between the frequency of the photon and the wavelength of the photon, or in this case you can think in terms even of electromagnetic waves. What's the connection? Anyone? This should be an undergrad first year physics. Energy, not quite right. There is an equation called dispersion formula. Sorry. Oops. I don't want to do that. Do you still remember dispersion formula? Where essentially there is to relate the phase velocity with frequency and wavelength. So this is written in terms c, the phase velocity of your electromagnetic waves, for example, is given by c, and then your frequency is written as nu here, and then this is yeah. Okay, I think everyone still remember that. That is probably in terms of your ordinary notation. This is phase velocity equals to frequency times lambda. Okay, so we use that to convert from the case of frequency to the case of your wavelength if you want to. Okay, so one can generalize this formula. Remember that this formula was obtained from the case where your electron initially is at rest. One could even have the initial electron to be in motion. In this particular case, you might try to get a different equation out. Okay, so what we do in this particular case is to look at the form momenta of your electron. Okay, so you take the scalar coming out from this form momenta after the collision. For example, over here, q2 mu, which is given by the rest mass of the electron square times c squared with a minus sign. Okay, and then you use an expression from for q2 mu from this what you call conservation of form momenta. Now one cannot assume. Oh, I got this wrong. Sorry. What am I doing? So this should be P1 mu plus P2 mu Q1 mu plus Q2 mu. Okay. So always remember the convention that we have adopted. So the P is the one before collision, Q is the one after the collision. So I got confused just now. So Q2 mu is the case of the form momenta after of the electron after the collision. Now you can bring this to the other side, and that gives an expression for Q2 mu. So this is essentially that. Okay, and then you have the covariant version of that, and then you just start multiplying each of this term out. So your P1 mu here will give you 0 because your this is essentially coming from the photon. So your rest mass is 0. So the same thing with Q1 mu coming from this times that, and that's 0. And then you have P2 mu, okay, which is the initial form momenta of the electron. Okay, and in this particular case, you're not assuming that your momenta is actually at rest, but it's actually moving. So but still, even if it's moving, the scalar that you get will be the same thing as the rest mass of the electron square times c square with a minus sign. So this will in the end will cancel off with that. And then what's left from the multiplication of these two quantities is the cross term. Okay, so you get P1 mu, P2 mu, P1 mu, Q1 mu, and P2 mu, Q1 mu, okay, with a factor of 2. So, and this is what's left because the rest cancels off, and you can re-express P1 mu, Q1 mu in terms of the other two cross terms. Excuse me for a while. Sorry. So you can get this term coming from the other cross terms. Sorry. So now one can start to put in the components of this Momenta. And in this particular case, we need to probably, I did not quite show this, but we can actually use the notation before, okay, without any assumption of what P is and Q is in this instance. So over here, P1 mu, Q1 mu is coming from the photons. So this will be just P dot Q for the three momenta of your photons over here. And then the fourth component with a minus sign will be just a magnitude. Okay. And then we have this. Oops, sorry. And then we have this, which is now in this case is your form moment of the electron before the collision. So this is given by the first three component is given by PE, and then the fourth component is given by the relativistic energy. Okay, and this will be contracted with the three momenta of these two things, and here is just your photons here. So this will be P minus Q, and then for the fourth component will be just the magnitude P minus Q. Okay. So again, on this side, you use the fact that one can re-express P dot Q in terms of your scattering angle, cos theta there. And over here, it gets a little bit complicated because of the momenta of the electron over here is involved. Okay, so that gives you, if you look at what's going on here, this will be come from your ordinary expression for, let me just check over here. PE is MeV. So that would actually let me try to recall where is this factor of 1 over C coming from. Okay, let me see. So what's your 3 momenta in this case? So for your 4 momenta, let me go back up. So I would have PE equals to, okay, I'm not quite sure what's happening here, but my guess there will be some modification due to the relativistic formula. I can't remember precisely what was the, let me go back to which lecture was this? Sorry, I can't remember all the formulas. So you just check how do we define your 3 momenta in this case. So your 3 momenta is given by the relativistic mass times the velocity. Now the relativistic mass is given by, I think there was another formula for your relativistic mass. It's given by that. Okay, so that would actually give you okay, let me just confirm this later on, because one of the things that seems to show up in this note seems to be the factor of 1 over c. So I just could not figure out where this comes from at the moment. But essentially it comes from, well, I mean, you just have your P equals to your P here will be your gamma ME V in a way. So how this actually simplifies to 1 over c at the moment. Okay, I will come back this maybe in the next lecture. Okay, but essentially this will become that. Okay. So there's also a factor of E over here. So there's a relationship. So it must have come from that E over C equals to ME C ME squared C squared plus P squared. So somehow or other, I'm using that formula together with this to get that. Okay. I will come back to this part maybe in the next lecture so that I can focus on the finishing off this formula first. Okay. So let me just assume that for a moment. Okay. And then this one will be just P minus Q with a minus sign will be just turned into Q minus P. And then finally, we divide everything by PQ. So that sort of make this factor disappears. I think I also divide it by a minus sign. Okay. divided by that. So that changes from cos theta minus 1 to 1 minus cos theta, and also they flip into your P minus Q here. So you get the result for the case of the Compton formula when the electron is not at rest is given by a modification over here. Here your capital P, this is capital P here, okay, is given by Q minus P, which is the Momenta transfer. Okay, so that is just the modification that appears when you have the electron in motion. Okay, so I think perhaps the thing that one should take from this is that the Compton formula is really coming from the idea of 4 momenta of the photon. So that's the main thing that you want to take the lesson from here. Okay, so that finishes off this lecture 12. Okay, so let's move on. Are there any questions at this stage? Apart from that expression for your 3 momenta of the electron, I will figure that out in the next lecture tomorrow. No question? Okay. So, right. So we move on to the next of lecture 13 here, which is really a different thing that we're going to go into. We will go into electrodynamics in the context of special relativity. You probably have done electrodynamics in a non-relativistic context through the case of Maxwell equations. So Maxwell equations in the ordinary vector form are given by a set of 4 equations. Okay, this is the divergence of the magnetic field. Okay, remember your electromagnetic field is really involves the oscillations of your electric field and the magnetic field. Okay, so in other words, the Maxwell equations that involves your magnetic field and electric field are going to be somehow coupled together. And in fact, this is actually shown here. Here is the divergence of your magnetic field here, and then here is your curl of electric field is related to the time derivative of your magnetic field. Okay. These 2 equations, however, are called Sorcery Equations. We shall mention why in a minute. Okay, so these are Sorcery Equations of your Maxwell equations, and then you have the other one, which is the divergence of your electric field. So in a way, this is like swapping your magnetic field here with electric field, and then in this particular case, we'll consider your electric field being swapped with a magnetic field. Okay, so your divergence of electric field depends on another thing, which is whether there's charge or not. Okay, so in this particular case, on the right hand side, if there's charge, then you write this as 4 pi rho, where rho is essentially your charge density. And this essentially talks about the source of the electric field. Okay, so that's why in this particular case we call this as a source equation. And for the other one, which has the curl of B, and then the time derivative of your electric field, this corresponds to another type of source, which is your current density. Okay, and both these equations are then called the Sorcery equation. One is talking about the current, okay. The other is talking about the charge. What else? Okay, the other thing that I should have mentioned also, there are, I think we have come across this before when we talk about units. Previously we talked about relativistic units, and then we talked about natural units. Relativistic units is when c equals to 1, and then natural units is to have both h equals your Planck constant equals to 1 together with your c equals to 1. So this is natural units. And then we sort of digress a little bit about the units being used in electrodynamics for historical reason. There are two different types of units being used. One is called the Gaussian CGS units. The other one is with the standard SI MKS units. Okay, and in MKS units you have this 1 over 4 pi coming in together with the epsilon naught. So this gets modified differently, and they are not equivalent. Okay, these units are not equivalent in the sense that it's a different set of units compared to this one. Okay, it's just a historical mix-up. You have all these different units inside electrodynamics. Okay, but that we will not ponder on this too much. We will just stick to this Gaussian CGS units, because then this thing will be replaced by just the factor of 1. Okay, so that's simpler in a way. So in other words, you get this all equation in terms of CGS units. If you want to convert this into MKS units, you might have this factor multiplied somewhere. Okay, so I'm not going to go into that. You can look it up in some textbook. So okay, now the most important thing about all these four equations, one is Sorcery equation and the other Source equation, is that your electric field and a magnetic field is essentially coupled together. So that already indicates that, okay, there must be a better way of describing these fields, okay, into a more unified form. Okay. So at this stage, we're still treating your electromagnetic field by considering your magnetic fields, electric fields separately at this current point, so that we can actually talk about potentials after this. Okay, so we will replace this by a much more unified notation, which is you have seen this before, which is given in terms of your EM field strength tensor. This we have introduced you earlier as an example of a tensor. Okay, but now we're going to go this in a more systematic way. Okay, right. What we'll do next is the following. We have another important equation that we need to derive from this Maxwell equation, which is essentially what we call the equation of continuity. Where does this come from? You can actually take the divergence of the last equation. Okay, so you take the divergence of this, the whole thing. Okay, so in other words, on the right hand side, you have the divergence of your current density. So you get del dot J here. So I'm going to multiply this whole equation by C over 4 pi. So I get C over 4 pi over here, and then I have the divergence on the thing on the left hand side. Okay, so that gives you del dot del cross B, and then del dot 1 over C d dt of the electric field. Del dot del cross B is going to be 0 by vector calculus, okay, and then that leaves us with this term which is given in terms of divergence of the electric field. But divergence of electric field is given by that. Excuse me. And you can replace that by your charge density, and then you find that this is equals to minus d rho dt, or partial rho partial t. Okay, so rearranging this equation, then you get this equation which is known as the equation of continuity. What is essentially the equation of continuity? I think you have met this before in so many different forms. Okay, so this is just an equation that implies the conservation of charge. Okay, just in other situation you have equation of continuity in quantum mechanics. Okay, it would be conservation of probability. In the case of fluid dynamics, your rho will be considered as your mass density, and J will be your flux or the mass. Okay, so fluid dynamics will be conservation of mass. Okay, so in this case it will be conservation of charge. Okay, so how can we actually understand this? It's actually the following. The charge inside a particular volume, say volume V here, can be given in terms of a triple integral over the volume, okay, of the charge density over the, with respect to the volume element. So here is a volume element. So how do you describe the rate of change of charge? Is by just operating this with a time derivative. So you take the total time derivative of Q, but when you go inside your triple integral here, your rho here will be a function of your x, y, z, and t. So in other words, when you go inside, the total derivative will be replaced by a partial derivative because you have other variables coming in. Okay, so you get partial rho, partial t times the volume element. Okay, so that will be the rate of change of charge. But now the partial rho, partial t can be replaced using this equation of continuity, which is given by minus del dot j. Okay, and then minus del dot j, so you bring the minus sign out, del dot j integrated with respect to the volume. You have done an integral calculus, vector calculus before in terms of integrals. This can be simplified using the Gauss theorem as essentially as a surface integral. Okay, so for a surface integral there will be some projection with respect to a direction of the on the surface. For example, here you can think of your j coming out here. Okay, and then on that on that surface element there will be a normal vector. So that will be that normal vector over here. Okay, and that can be interpreted as the current density going out means it's like the charge is actually moving out. Okay, the rate of change of, remember the rate of change of charge, okay, will be just your current. Okay? So in other words, this is essentially what we call the flux, okay, the flux into the system or out of the system, and that will be the flux of what? Flux of charge. Okay, so in other words, if your if there is no flux going out from the volume that we are considering, then essentially this will be equals to 0. Okay, so no flux, meaning no charges leaving or entering the system, no flux, that means J equals 0. Then essentially this will give you d dt q to be equals. So that's why it's related to the idea of conservation of charge. If there is flux, that means d dt of q will not necessarily be equal 0, but you can have changes due to the possibility of charge coming in or charge going out. So there will be what I call change of the charges which is contained inside this particular volume. So that's how we think about this particular statement of your continuity equation. Okay. Okay. I think it's almost time's up for this particular lecture. So let me continue to the next lecture tomorrow for the rest. Okay, so let me get your attendance today. Okay, any question before we leave? I guess not. So we'll see you tomorrow. Okay, thank you.